All right. Hi, everyone. Again, welcome back to another lecture in mathematical methods. Today, we're going to look at something a bit more statistical, a bit more advanced in terms of statistics. It's sampling. All right. So, some of you may have looked at this before, but it is a bit of a tricky concept. So, we're going to go through it a bit slowly and we're going to use examples throughout. Okay. So, our first example is imagine you're a content creator or a music artist, okay? So you are a music artist, okay? So obviously you want to make songs and you want to put them on some platform, all right? So you want to know what's a good song. So one way is to look at the songs on the platform and see what does good, okay? You think that a good catchy chorus is is the factor for success in the music industry, and so that is your kind of that is your bottom line. So if the song has a good catchy chorus, that'll be a hit. If it doesn't, that'll be not a hit. Obviously, it's more complicated than that, but for our purposes, let's just say that's the case. So obviously, the platform has billions of songs. Okay, so let's say it has billions of songs. Okay, so to find out what type of choruses are catchy, you can't just go through every single song. That's very impractical, takes too much time, and just can't be done in general. Okay, so too many songs. So what you can do is take a sample, okay, or take a smaller portion. So we take a sample, which is a smaller portion of the songs. Okay, great. So we have a sample. Let's say our sample is 20. So we take 20 songs and we analyze them. Much easier, much smaller, and maybe it tells us something about the entire list of songs. Okay, so 20 songs, and we find that 5 of them have a catchy chorus. Okay, which means that 5 out of 20 songs have a catchy chorus, which is about 25%, I think. All right, so using this, you can estimate that out of the billions of songs, 25% of them have a catchy chorus, and therefore 25% of them have a hit. All right, but is this really that straightforward? Is it really true that 25% of the songs are hits? Maybe, maybe not. But what if you take another sample? Okay, this time you take another 20 songs, let's say. Okay, and you get maybe 10 of them have catchy choruses. Okay. Well, now what? Based on this one, do you go that it has a 50%? That all of the out of all of the songs, 50% of them have a catchy chorus, or what can you say here? Okay, and the more you do, you realize that it changes a lot. Okay, you see that sometimes it's 50%, sometimes it's 25, sometimes it's 30, sometimes it's even 0. Okay, so there are variations within your samples. Okay, now this is a key thing about statistics. Okay, key thing is that samples vary. Okay, and there is almost nothing you can do about it. The one thing you can do to reduce the variation is to increase your sample size. Okay, so think about it. If you have 100 songs and you do 5 of them, it may not be a good indicator of the actual 100. But out of the 100, if you do 99 of them, probably a very good indicator, right? But often, for example, in this case, it's very infeasible to do that. Okay, you can't go ahead and look at every song in the billions. Okay, so you have to take a smaller portion, which is what we did. And in taking that portions, they vary. Okay, if they are randomly selected, they would vary between each other. Okay, so because they vary, it's hard to predict the actual population from it. Okay, and that is what we are going to look at now. All right, that is what we are going to go into in the upcoming little bit, and which is mainly what we're going to focus on. Okay, so like I said, let's we take samples, we do all of this stuff, and we have problems. But often, when you take samples, there won't be like this, okay? Most of the times when you take samples, it will be like taking batches, okay? So for example, imagine you work in some sort of factory, okay? Cool. So look at analyzing the factory, for example. All right, so the factory produces cans, okay, which are labeled as 375 milliliters of drink, okay? Any drink, whatever you want, all right? So you are there, you want to do a quality check, okay? Obviously, again, it produces a lot of cans every day. You cannot go through all of them to make sure it's working fine, okay? But what you can do is you can take samples, all right? So say you take samples here, and here, what you will do is you won't take a single sample and see if it's good. You will take multiple, like you take like a batch of maybe 10, okay? Or a batch of 5, a batch of something like that, okay? And then you use that batch and then you analyze it, okay? So for example, you get this as your readings, okay? Sorry. Let's just put in some random numbers. It doesn't really matter what they are, as long as it makes sense to have them there. Let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so this is, for example, say the batch you get, you look at this, these are the values you get, okay? Now, how can you use this to see if the factory or the machines are producing properly, okay? Here's where some of the maths starts to pop out. Here's where it starts to get a little bit technical and tricky, but bear with me, we're going to get through this very easily. All right, so this sample, I'm going to start calling it a sample now. So this sample it's going to have a mean, okay? And it's going to have a total, okay? So the mean is obviously the average of all of these values. Total is the total of all of these values, okay? Now, remember what I said before, that samples vary, okay? So if you take another batch of 10, it would have a different set of values, so it would have a different set of means and standard deviation, but it would have mean and sum, okay? It would have its own mean and its own sum, all right? You do that multiple times with different samples, you get different results, okay? And you find something very interesting, that the mean you get is distributed in a way, okay? It's not completely random, all right? You find that this sample mean, which I will say is x bar, okay? That's how you technically call it, for n samples, and I'll start calling this as n, as in the sum of the samples, all right? You start seeing that they are distributed in a way, okay? And these distributions for the sample means and the sample sum have their own means and standard deviation. So remember that a distribution is simply how variables are being produced, okay? How can you predict them and their probabilities and all of that, okay? So these sample means and sample sums have their own distribution with their own mean and standard deviation. Now, how do we find that? We use what's called the central limit theorem. Okay, so we use the central limit theorem. Okay, now what is this? It states that as n gets bigger, so as the number of samples gets bigger and bigger, okay, x bar of n gets, actually, I should rewrite this. I'll say if n, so again, the number of samples, is sufficiently large, okay, so if n is big enough, x bar of n has a mean. So notice how I was saying that the sample mean has its own sample means distribution, has its own mean and standard deviation. The x bar mean is, let me just make sure I don't get this wrong. It has a mean of mu. Okay, mu being the mean of the population. Okay, and it has a standard deviation of sigma over square root n. Again, sigma being the standard deviation of the population and n being the number of samples. Okay? It also says that if n is sufficiently large, S of n, so the sample sums, the total of each sample, has a mean n mu, okay, so n times the population mean again, and has a standard deviation of mu square root n, okay, sorry, sigma square root n. So there is your mean and there is your standard deviation. So, but you might be having this question, what does it mean for n to be sufficiently large? So if you have looked at this course before or looked at some textbooks, you would see that it says if n is greater than or equal to 30 or 10, something like that. That is incorrect, okay? That is completely wrong. You cannot say what n should be to be big enough, okay? You cannot tell that unless you know stuff about the population itself. And most of the time, you don't, okay? So the way to know if n is big enough is typically you would have some sort of histogram or something that shows something like this, okay? So for example, you have something like this. This is x bar of n, and it's this histogram, okay? So let's say this n is 25. The way you use it, use the central limit theorem, is you look at this and you're like, okay, so I am seeing that the sample means are approximately normally distributed, okay? That is, sorry, I forgot to mention that actually. That is one of the key things of the central limit theorem, is that these two become approximately normally distributed. Sorry, I'm very sorry. This is actually important. Approximately normally distributed, and they get those means and standard deviation. Okay, standard distributed. Okay, so I'm saying that as n gets bigger and bigger, all right, these get more approximately distributed, and they get their means. If you look at this one, you can say that, yeah, it's kind of approximately distributed. So the question is n equals 30 big enough? Well, yes, in this case, because at 25 it was approximately normal, at n equals 30 it would be even more normal, and from there, yes, you can use your formulas and you can get into the nitty-gritty of the means and samples. At the same time, if you have something like this, you know, for x n equals 10, all right, and then they ask, is n equals 15? Do we consider that as n big enough? Well, no, because you can't really say. This is not approximately normally distributed, so you can't really say anything about n equals 15. So you can't really use the formulas. The take-home message is what it means to have a sample sum and a sample mean, and what it means to use the central limit theorem. Okay? So the central limit theorem states that as n gets bigger and bigger, sample means and sample sum become approximately distributed. Okay? And if n is sufficiently large, x bar of n has this mean and standard deviation, and the sample sum has this mean and standard deviation. That is the take-home message from this entire lecture, and hopefully that went well. If there are any questions, just let me know. But it is very important to practice this properly because it can be a bit of a tricky concept. So we will look into that. Please be there for the exercise part of this topic because it's going to be very useful. All right, it's going to have some nuggets from the exams, and it's very important to be there. All right, so see you then.